Hello, I'm Sophie Rovner from the American Chemical Society. Welcome to this news briefing from the ACS's 256th National Meeting and Exposition in Boston. We're joined today by Dr. Nicole Zander from the Army Research Lab. She's studying how water bottles and other recycled 3D printing materials could help avoid military supply snags. Dr. Zander.
Thank you, Sophie. The research I'm presenting at this year's ACS meeting is performed under our Additive Manufacturing Polymer Feedstock Development and Processing Mission Program. The goals of this program are to push the boundaries of polymer additive manufacturing to increase cohesive properties such as strength, flexibility, and toughness, and also develop new capabilities for expeditionary additive manufacturing, which is my particular area of research. Ultimately, we wish to develop structure processing property relationships for polymeric materials prepared by additive manufacturing and enable the production of high-quality polymer and composite parts for the Army. The motivation for this work is to improve the safety and operational readiness of the soldiers, who are often stationed in remote locations where it can be difficult to obtain parts quickly due to transportation across the globe and through conflict zones. Additive manufacturing enables on-demand fabrication of such needed repair parts, and by utilizing waste plastics, the self-reliance of the warfighter on forward operating bases can be further improved by reducing supply chain dependence. At the same time, waste and supply removal costs can be reduced and sustainability increased. The work I will present details the experimentation conducted to turn waste plastics into polymer pellets that can be extruded into filament for use in material extrusion or fused filament fabrication type of additive manufacturing. A variety of plastics, blends of plastics, compatibilizers, and fillers were evaluated to determine the range of possible mechanical properties from such indigenous and scrap polymeric feedstocks. The effects of fillers such as cardboard and wood to provide reinforcement and reduce warpage or impart additional functionality was also examined. Blends of recycled plastics were explored to enable tailoring of mechanical properties to need. Recycled PET was found to have similar mechanical properties to common commercial filaments such as ABS and polycarbonate ABS, and was demonstrated to be a suitable replacement for a vehicle radio bracket, which is a long lead military part. The radio is typically replaced when the bracket breaks at a cost of $200. I think I have the bracket up on the right of the slide there. Material properties and functionality could be further improved with appropriate fillers and additives. A major highlight of this work involves the transition of the processing we have done in the lab to an expeditionary polymer processing laboratory in collaboration with the Marine Corps. All of the equipment to do the cleaning, shredding, extruding, and printing has been designed to fit in a 20-foot ISO container and run off a standard generator. We are hoping to secure funding to demonstrate the lab this coming year. Thank you for your interest, and I'll gladly take any questions.
If you have any questions, please state your name and affiliation.
Hi, so it's Kath O'Driscoll from Chemistry and Industry magazine. I'm interested, I guess the novelty would be this idea of taking the waste plastics and producing pellets from them. Is that correct? And can you just say a little bit more about how it is that you're able to use these in situ? Is this something that we're going to be able to use? Could it be adapted for the home, for example?
Absolutely, and in fact, there are people who are doing something similar in their garages currently with, self-built extruders. With some of the materials, you're able to, particularly ABS, which is a commercial material, but a lot of times you'll have failed prints, so people will recycle those failed prints and re-extrude the filament to put back in their printer. So I'm basically just trying to do this with consumable plastic materials. So some of the materials are a little bit more difficult to work with than ABS, but I think that this could be something that could potentially be adapted to home use or definitely used off of forward operating bases.
But could you just say a little bit more about the actual what it is, how you're able to do that, to produce the pellets and to produce the filaments?
Yeah, so it's actually a fairly straightforward process. We take something like a water bottle and we shred it into, small particles and dry the particles, clean and dry the particles, and then run them through an extruder. And then we can, with the dye setting to the setting we need for our 3D printer, we can extrude filament. that is the feedstock for the printer.
So in terms of energy to run that process, is there a lot of energy required or a temperature? Is it?
Yeah, so I mean, the extruder will require some energy, but what I'm using right now is a benchtop extruder that's about this size, so it's actually a pretty small scale system. But I potentially think this would make sense to scale it up so we can use a lot more of the trash materials available. But yeah, it's pretty low energy process.
What scale do you imagine it will be kind of useful at?
Well, I think, we want to maybe consider construction materials and much larger materials, but that will obviously need to be, we will take the pellets and not use filament. So there are some new companies that are making very large-scale pellet printers, like at Oak Ridge National Labs, where they're 3D printing cars and things along that line. If we can use recycled materials, that would be a lot of costs and energy savings.
Thank you.
So we have an online question from Doug Dollamore from ACS. He says, I believe you recently conducted field tests of this new technology in Afghanistan. What did you learn from these field tests, and what modifications, if any, might be needed?
So unfortunately, that is incorrect. We have not fielded the prototype, but we are very much hoping to do so in the next year and get the feedback loop going so we can kind of understand how we need to modify our technology to make it useful in field conditions.
Okay, good. And also, I see that you have some things on the table, or do you have some things to show us?
Yes. So I brought that long lead part radio bracket. So here is a bracket, and it's actually bent because it's been tested. So we tested it in a custom fixture for 3-point bending mode. And this we compared against a bracket printed from commercial filament that they commonly use on the battlefield and found similar load at failure, which was really exciting for us, kind of our first demonstration of the technology. I also have a functional tool. So this is a 55-gallon drum wrench to open 55-gallon drums, because often they don't have that available, and it's very challenging to open these drums for fuel and other things in the battlefield. So although this may break upon the first or second use, it could be easily reprinted. And then I also have this is a training aid for an explosive ordnance technician training, so they can take these and then they'll spray paint them and they'll be able to put them and do training exercises. And so that's something that, is sort of a non-critical but essential part that you could use these plastic filaments to print.
Laura Cassidy with ACS. How did you decide what objects to print, and are there certain objects that are more amenable to this than others?
So it's actually I've been focused on long lead parts, because most of the plastics, especially with the FDM or fused deposition modeling process, are not as strong as injection molded parts, and a lot of the plastics are not engineering plastics when you consider like recycled polypropylene and polyethylene. So I was looking at non-critical parts, and one of the major issues is the long lead parts that can take years, or sometimes the parts aren't even available. So that kind of, to me, was where this technology could be the most useful. But I've had some issues tracking down part files for a lot of these parts, so mostly they were selected based on the files that I was able to get and of the size scale that I could print with my desktop printer.
You mentioned you were functionalizing these polymers as well to improve their properties. Can you say a little bit more about what exactly you've been doing to functionalize them? Is that made sort of the pellets that are then incorporating functional
Sure.
attachments?
So at this point, I'm not doing any kind of chemical modification, but I am reinforcing some of the materials. So polypropylene is widely available on a forward operating base if you consider, yogurt containers, cottage cheese containers, things of that nature. But it actually has pretty weak tensile properties. So I've been reinforcing it with cellulose-based materials and had very large improvements in the modulus and tensile strength of the materials by incorporating cardboard, wood flour, or waste paper. And I do that in a solid state shear pulverization process. So I actually change the screw configuration on the extruder and run it cold, so you actually get a powder that then you can melt process. So if you think about Trex decking or something along that lines, I'm basically making a 3D printing filament like that. Which is a lot stronger. And also it does not warp as much. So polypropylene, polyethylene are subject to warping when you're 3D printing, and so they're actually not commonly sold as a commercial filament for 3D printing, but when you add reinforcing materials, you can improve the shrinkage and warpage of the materials.
By how much can you sort of improve these properties?
So we are still collecting the numbers, but in terms of we're still collecting the tensile data. We have storage modulus data from dynamic mechanical analysis, and we're looking at 30 to 50% improvement in storage modulus with 10 to 20% loading of cellulose-based materials. So pretty substantial.
And what sorts of things would these be useful for?
So again, we're looking at non-critical items, a lot of brackets, clips, things to fixture materials. So sort of your small parts that are seemingly not important but are actually quite essential to like making the soldier have their backpack fit more comfortably or be able to carry their water bottle. And when you consider, they're out for 12 hours at a time with carrying 70 to 80 pound loads, even a small clip to make something fit better can make a big difference in their safety.
I think you mentioned that the radio bracket would cost $200 or something, which is great. So how much can you produce it for? I mean, what sorts of cost savings would you be looking at?
So it's the replacement of the radio itself that is $200, not the bracket. But the issue is you cannot get the bracket very easily. So it's easier to get the radio than to get the replacement bracket, which is a common problem with a lot of these government parts. So, but the bracket, takes about an hour to print, maybe 10 water bottles to produce enough filament to print the bracket. So essentially, the bracket cost is free minus any of the labor costs.
So big cost savings then, potentially.
Yeah, potentially.
Okay. Thank you.
Perle Buslig, ACS. When you're recycling these materials, is there a limit to how many times you'd recycle, and what kind of loss in strength are you getting in successive recycles?
Sure, that's a good question. So far we have not looked at loss and tensile strength, but we have looked at rheological changes over 3 extrusion cycles, and we see it to be fairly stable. We see about a 5% decrease in viscosity with a 3rd extrusion cycle. So some of the polymers I think are going to have issues quicker than others. I've seen some papers where certain polymers like PLA or ABS can maybe be recycled 5 to 10 times without significant loss. With PET, I think as long as the material is carefully dried each time, we can probably go 5 to 10 cycles as well, but that's yet to be determined.
Now, when you're recycling these things, do you use just the recycled material, or do you always supplement it with the fresh stuff, so
Sure.
you basically have a kind of a backup strength there?
Sure. So no, it is 100% recycled material at this point, yes. The exception is some of the blended polymers. I've added 1 to 5% of a compatibilizer to allow some phase mixing of the incompatible polymers.
And in practice, what kind of lifetimes do you expect? Obviously not to replace the real thing,
Right.
but what's an acceptable lifetime for recycled?
So we consider these to be temporary parts, not replacement parts. I think that we need to do further research and potentially explore intelligently supplied feedstocks, some of the higher engineering grade polymers like Ultim. Perhaps we can find that we can recycle those 20 times, and it would be worth supplying those to be permanent parts rather than replacement parts.
Thank you.
So I noticed that there's a color gradient here. What does that mean? Or what caused that?
Right, so it could be the source of the bottle. So some of the bottles have a little bit more of a tint to them, so we can get different coloration based on the source.
And how much training would it take would it be a soldier ultimately doing this?
Yes. Yeah, so it would be soldiers that would be trained. I foresee that this laboratory would be on you're on the right side, okay. It would be on like a larger forward operating base, so maybe there'd be some sort of long-term staff that I could sort of train the trainer. But yeah, I do foresee that soldiers would be able to be trained. It may take a couple weeks, and I would likely have a detailed SOP where we would demonstrate, we would train on just one polymer, one process at least to start, and then additional training could be provided depending on their need and interests. But I've been on a lot of innovation challenge opportunities with the Marine Corps, and they've had mobile training labs, and I've seen soldiers new 18-year-olds who've come and learned how to do welding and built a scooter in just in one day. So it's amazing if you can get motivated people, even if they don't have specific, engineering or scientific background, that they can be able to be trained in these new technologies and put them to use.
You mentioned in the press release that you'll be building a mobile recycling trailer for this.
Mm-hmm.
Can you talk about this? And will soldiers basically drop off their used plastics and then, pick up their new parts later in the day?
Yeah, so the slide here is showing the design of the lab, and basically we would have a industrial scale dishwasher to kind of clean the materials. We'd have a industrial scale reclaimer that would shred materials, including like failed prints, 3D prints, and then we would have a vacuum oven for drying of the plastics, and then we have our extruder set up and a 3D printer. So basically all in one 20-foot, 20 by 8-foot lab, you could do this entire process. We foresee probably paying civilian populations to do some of the plastic cleaning and sorting, because that's typically something that the military likes to engage in. So I think that could be useful for time and cost savings. But yes, essentially we'd be taking packaging from the shipping dock and the cafeteria and using that as our feedstock for making parts.
All right, thank you very much. The archived version of this session will soon be posted at bit.ly/ACSLive_Boston 2018. Please join us for our next press conference at 3 p.m. today on weaponizing oxygen to kill infections and disease. Thank you.